Hello everyone, and welcome to our talk on self-stabilizing uniform reliable broadcast for the NETYS2020 conference. We consider distributed message passing systems with n asynchronous nodes that are prone to crashes as well as packet failures. In such systems, reliable broadcast is the most fundamental task. This work considers a variance of reliable broadcast by Adselicus and Twig. Here, if a node, faulty or not, delivers a message, then all non-failing nodes also deliver that message. We specify it using the following properties. Validity. There is no creation or alteration of URB messages. Integrity. There is no duplication of URB messages. And termination. If the broadcasting node is non-faulty, or if at least one receiver, faulty or not, URB delivers a message, then all non-failing nodes URB deliver that message. Since we don't care if the receiver node is faulty or not, and we still require termination, that's the reason this protocol is called Uniform Reliable Broadcast. Unlike earlier work, this paper considers the design criteria of self-stabilization. Self-stabilizing systems can recover after the occurrence of transient faults. Transient faults can model any temporary violation of assumptions according to which the system was designed to operate. This includes, for example, the corruption of control variables, such as the program counter, or timestamps that the algorithm is using. But this also covers operational assumptions, for example, that at least a majority of the nodes never fail. Such violations, according to our model, can bring the system to an arbitrary starting state. Dijkstra considers systems that are required to recover from any starting state. After that, the system run must return to a correct behavior, or as we call it, a legal behavior, within a bounded period. This slide brings more details regarding our fault model. We consider both transient failures and permanent failures. When it comes to permanent failures, we consider detectable fail-stop failures. Transient faults are considered to be rare, but the more frequent case considers packet failures. It can be omissions, duplication, or reordering, as long as the communication is fair. That means that every message sent infinitely often is received infinitely often. This model itself assumes that the system can start from an arbitrary state. During the recovery period, the execution must be fair. That means we can only have packet failures, but not node failures. After the recovery, the system is by definition required to be in a legal execution, and that means that all benign failures are possible, both packet failures and detectable node failures. Our contribution includes the first self-stabilizing algorithm for uniform reliable broadcast. Compared to earlier work, our algorithm slightly increases the communication costs, because periodically every node sends a small gossip message to every other node in the system. However, one can balance the trade-off between the stabilization time and such communication costs. We focus on a quiescent uniform reliable broadcast algorithm. By quiescent, we mean that every broadcast operation incurs a finite number of messages. We also show how to bound the system state using a novel flow control mechanism that we are not aware to be available for self-stabilizing systems. Our technical report also includes an extension for FIFO delivery order.
We now turn to review earlier work in the area. We're going to look at a number of non-self-stabilizing algorithms, and this will help us to understand how a self-stabilizing algorithm should be designed. We note that in the absence of failures, one can simply substitute every broadcast invocation with a most straightforward broadcasting mechanism that simply sends the message to every other node in the system. When that message arrives, the receiving node simply raises the delivery event. Here's another rather simple non-self-stabilizing algorithm. This one assumes that node may crash. However, the communication channels are reliable. Here, whenever the broadcast operation is invoked, the processor is sending a message to itself. Upon message arrival, either due to self-sending of the message or from any other node in the system, the receiving node tests whether this message was processed before. If this is the first time, the node sends the message to everyone other than itself and the sending node. After that, that message can be delivered. Next, we review another non-self-stabilizing algorithm. This algorithm can tolerate both unreliable communications and, at most, a minority of node failures. Upon the invocation of a broadcast operation, the node again sends the message to itself. Upon arrival of such message from processor PK, processor PI tests whether this message was processed in the past. If it was processed in the past, then the only thing that node PI needs to do is to store the index of the sending node. If it is a newly arrived message that was not processed in the past, the node simply stores the ID of itself and of the sending node and activate a task called diffusion of message M. Here, there is a do forever loop that is going over all the active tasks for diffusion of a message. For each processor that is not part of the set of received by, meaning it has not sent before to processor PI a message, processor PI needs to send that message. Whenever there is a majority of nodes from which we received an acknowledgement for message M, processor PI can deliver that message if it was not delivered in the past. Note that this algorithm never stops sending messages. And if we wish to have a more communication conservative algorithm, we have to consider the next algorithm. We are going to look into two non-self-stabilizing Quiescent URB algorithms. The first one uses perfect failure detectors. Just like earlier algorithm, the invocation of a broadcast let the node send a message to itself. Upon the arrival of that message, if this is the first time, then the node simply allocates a task for diffusing the message. If this is not the first time, the node simply aggregates the ID of the sending node. Unlike earlier algorithm, here the receiving node needs to acknowledge the arrival of the message to the sending node. Upon the arrival of that acknowledgement, the receiving node also stores the index of the node that have sent the acknowledgement. In the do forever loop, for every active diffusion task, the node is looking for neighbors that are trusted and from which it has not received yet an acknowledgement for message M. If such a node exists, then it sends a message to every such node. Moreover, it tests whether the set of trusted processors are a subset of the set from which the node has received acknowledgement for that message. If this is the case, and the URB message of M wasn't delivered yet, then the node can deliver that message. Our second non-self-stabilizing Quiescent URB algorithm uses eventually perfect failure detectors. Just like earlier algorithm, we see the self-sending of a message. Upon the message arrival, the node aggregates the ID of the sending node if this is not the first time. If this is the first time, there is the allocation of the diffusion task. After this allocation, the node needs to acknowledge the arrival of this message. Upon the arrival of the acknowledgement, the sending node also aggregates the index of the acknowledging node. In the do forever loop, we see the use of the heartbeat failure detector. Here, in line 32, if there is a trusted node that has not acknowledged yet, the node can send a message to it only if there is a need to, according to the failure detector. In any case, as we see in line 35, if all trusted nodes have acknowledged and this message was not delivered yet, then it's time to deliver the message. We are now ready to present our self-stabilizing Quiescent URB algorithm. Before we do that, we use an unbounded version of the algorithm. The algorithm uses two variables, one for sequence numbers that records the index of each message, and another one which is a set that describes the buffer of the node. Each record in the buffer is basically a tuple that includes the application message, the ID of the sending node, the sequence number that the sending node has associated with this application message, a Boolean flag that indicates whether this message was delivered before, and the set of received by that was described earlier, together with the vector previous heartbeat that was also described earlier. Upon the invocation of a broadcast operation, the algorithm first increments the sequence number and then call the function update. The function update tests in line 41 whether there is a record that includes this message. It does so by checking whether the message index appears in the buffer. That is, the ID and the sequence number, they are a pair that together uniquely identify each message in the buffer. If that record didn't appear in the buffer, the algorithm adds a record to the buffer while initializing the field delivered, as well as the set of received by together with a vector of previous heartbeat. If this message already appeared in the buffer, then all that is left is to update the field received by. The do forever loop starts with testing for stale information, that is, two messages with the same message ID. If this is the case, line 45 empties the buffer. The for each loop scans all the records in the buffer. If it finds in line 47 that the field received by includes all the nodes that are trusted, and if the field delivered indicates that this message hasn't been delivered yet, the algorithm delivers the message and mark this record as a delivered one. In lines 48 to 50, the algorithm samples the heartbeat failure detectors and then decides whether to send a message that for which there is no acknowledgement according to the indication of the heartbeat failure detector. Upon the arrival of this message, the receiving processor updates the local states and sends an acknowledgement. The reception of this acknowledgement in line 53 also calls the function updates. Going back to the do forever loop, we see that the algorithm is sending gossip messages with a maximum sequence number to all the nodes in the system. This allows in line 54 to the algorithm to make sure that processor Pi has the maximal sequence number with respect to all the sequence numbers that are related to processor Pi in the system. The correctness proof shows that within a bounded time, the system reaches a legal execution during which the system behaves according to its requirements. That proof assumes a fair execution, but this is only for the sake of recovery. The other part of the proof that considers closure does not require fair execution. Now we turn to explain how a self-stabilizing flow control mechanism can help us to bound the number of records in the buffer. On the left, we see the sender, and on the right, we see the receiver. The unbounded version of the algorithm makes sure that the sender's highest sequence number is not smaller than the one of the receiver. This you can see in the top arrow. The receiver PK can make sure that it stores at most buffer unit size records per sender PI, where buffer unit size is a predefined constant. It can do that by making sure that its buffer doesn't have too many records. That is, it calculates max sequence number of I minus buffer unit size, and this number allows it to make sure it has the right number of records. It can also store the latest receiver side absolute sequence number that it has for all messages arriving from PI, where an absolute sequence number is a number of the highest delivered message such that all of its smaller sequence number messages were also delivered. The receiver PK can then inform the sender about this value, and the sender will store it on the sending side obsolete sequence number with respect to packets arriving from the receiver K. By taking the minimum of such values for all trusted receivers PK, the sender PI can calculate the minimum sending side obsolete sequence number, and this value can bound the sender's buffer. So far we described a flow control mechanism that can just as well be non-self-stabilizing. Now we add the details that allows the mechanism to recover from transient fault. For example, due to a transient fault, the value in Tx obsolete sequence number can be greater than its correspondent on the receiving side. If that happens, Pi will ignore all values that are coming from the receiving side. In order to overcome this, Pi can repeatedly gossip its values to the receiving side and make sure that they are as high as the values on the sending side. Similarly, due to a transient fault, PK might be missing a message. And this is why the sender repeatedly sends the smallest message that it knows that PK might need. Other ways to deal with the transient faults is by asserting a certain invariant that we specify in the slide. In case of a fault detection, the sending side can just make sure that Tx obsolete sequence number uses the most recent sequence number of the sender. We now turn to explain how to bound the counter values and the sequence numbers. Transforming a self-stabilizing unbounded algorithm can use earlier techniques that exist in the area. In step 1, each processor that encounters a sequence number equals to max int disable the invocation of new operation and start gossiping the maximal index value together with the system state. While it receives messages from others, it merges the arriving values with its local ones. Then in step 2, all nodes wrap around to the 0 value by performing a global reset and replacing the sequence number, the highest sequence number, with the value 0, which is the initial value. This way, they can keep the same state while refreshing the system resources. After this is over, all new operations are enabled. We presented the first self-stabilizing uniform reliable broadcast algorithm. We also explained how to bound the system state. Our algorithm has a FIFO order delivery extension that can be found in the technical report. There is also yet another extension called the Set Constraint Delivery Broadcast, which is to appear in the ICDCS 2020 conference. This extension, as you can see in the figure here, is building on top of the reliable broadcast with FIFO order delivery. And Set Constraint Delivery Broadcast can support atomic multi-reader, multi-writer snapshot algorithm as well as sequential consistent counters. We appreciate your attention and would like to encourage you to look at our technical report. Thank you.